Hello everyone, I am Aman Goyal, a PhD student at University of Michigan, working with Professor Karim Sakala. Today I will talk about a new way to verify distributed protocols, fully automatically, along with provably correct guarantees by using the concepts of symmetry and quantification. So let's get started. Here is an example of a simple multi-signature smart contract used in cryptocurrencies like Ethereum, Cardano, etc. This is the state transition diagram of each validator in the network, where the validator collects signatures corresponding to a proposed transaction, and if enough signatures are authorized, the validator approves the payment to the recipient. If instead the deadline has expired before enough signatures are collected, the transaction is aborted. We can encode such a protocol in a language like TLA+ or IV and then verify its correctness. But first, why do we want to verify such protocols? Examples include to avoid outages for cloud computing and other services built on top of these protocols. For example, Amazon recently faced an outage that was triggered when adding new nodes to their distributed network. Or to avoid cryptocurrencies and security hacks that may cost multi-million dollars, like the very recent ForceDAO hack, which allowed hackers to call the deposit function of the smart contract, even if they do not have any tokens. Verification basically boils down to checking safety properties, whether a safety condition is always followed or not. For example, in the multi-signature smart contract, we have three properties, P1, P2 and P3. Here are their English descriptions as well as their logical formulation. P1 says only cancel the transaction after the deadline has expired. P2 says make a payment only if we have enough signatures. And P3 says that the payment recipient is always the one that is proposed in the transaction. I will talk about a technique and a tool called IC3PO, which can verify distributed protocols fully automatically. For example, given the multi-signature smart contract and its three safety properties, in less than 30 seconds, IC3PO verifies that these properties are always obeyed for any number of validators, recipient, value, etc. And it does so by automatically deriving strengthening assertions A1 and A2 that together with the properties form a quantified inductive invariant. Here assertion A1 says we can collect signatures only if proposed, and A2 says all signatures collected are authorized. Here is a summary of the key ingredients of the technique. We use finite-domain model checking instead of directly verifying the unbounded protocol. And the basic intuition behind this is, as stated recently by Leslie Lamport, the 2013 Turing Award winner in the TLA+ Google group. Quote, "It is rare for an algorithm to be correct for a set of 3 elements and not for a set of 1000 elements." IC3PO also uses the protocol's inherent symmetries to perform scalable verification through symmetry-aware clause learning. And it relates these protocol symmetries with quantification to learn compact quantified clauses. It also analyzes finite conversions to check whether we have reached the cutoff size. That is, have we considered all behaviors of the protocol? We will talk about each of these concepts in detail. But first, let's cover the basics. Model checking is widely adopted for hardware verification, where techniques like incremental induction are used to prove or disprove the property with the help of SAT or SMT solvers. And the high-level idea is that the verifier is fully automatic. As we push the button, the verifier performs some kind of automatic analysis and exploration of the state space, and finally outputs whether the design is okay or says no, you can fail the property. If the property can fail, the verifier produces a counterexample trace that shows how to reach the bug from the starting point. If the verifier says, hey, everything is okay, with incremental induction, we also get a proof certificate. That is, an inductive invariant that mathematically explains why the design always obeys the property. And both the counterexample traces and the proof can be checked independently to guarantee provable security. Model checking has scaled significantly over the last decade and is now routinely used in hardware verification. Here is a shameless plug showing our hardware verifier AVR declared the overall winner in last year's hardware model checking competition, winning the competition with 7 gold medals. Let's very briefly recap incremental induction, which is also referred as IC3 or PDR. Incremental induction uses search solver in a unique way to perform an approximate reachability analysis with one-step queries. And the basic step involved is, can we go from the current approximation f to a buggy state in one step? If the property is already inductive, the solver should return unsat. However, generally speaking, the property is not inductive, in which case the algorithm looks at the solution to the query, referred to as counterexample to induction. And if this CTI is unreachable going backwards, we learn a clause to refine the over-approximation. Let's not go into the details and go back to the distributed protocols. Distributed protocols are a class of parameterized systems where a bunch of components exchange messages to perform some kind of activity. For example, a bunch of voters may vote for different candidates, and if a candidate gets enough votes, it is elected as the leader. The main challenge in verifying distributed protocols is that the domain is infinite. That is, we want to verify for any number of voters and candidates, and this results in the state space being infinite as well. Therefore, automatically verifying them becomes impractical very quickly, with automated reasoning becoming undecidable in several cases. Let's understand the high-level flow of IC3PO first. Given the unbounded distributed protocol, the property, and an initial size, say 3 voters and 2 candidates, IC3PO first creates a finite instance of the protocol. It then performs on this finite instance what we call SymIC3, that is, symmetry-aware incremental induction, which extends the normal incremental induction with the knowledge of symmetry and relates symmetry with quantification to perform quantified clause learning. If a counterexample is encountered, we get an execution trace showing how to reach the bug. Else IC3PO derives a quantified inductive invariant. The next step is to check, have we reached cutoff? Have the protocol behaviors converged? If yes, IC3PO outputs the quantified inductive invariant as an inductive proof for the unbounded protocol. Otherwise, IC3PO automatically goes to a higher size to include protocol behaviors missing in the current finite instance. Let's understand this procedure with a simple example. Here is the TLA plus representation of a simple protocol called toy consensus, originally written by Ken McMillan. We have 3 domains here, node, quorum, and value, and 2 state variables, vote and decision. Line 4 defines the quorum intersection axiom, that is, each quorum is a set of nodes, and each pair of quorums have at least a node in common. We have 2 definitions here, did not vote and chosen at, which are used in describing the 2 actions, cast vote and decide. A vote n can vote for a value v if n did not vote for any value, and a value v is decided if there is a quorum of nodes such that v is chosen at that quorum. At the bottom, we have the initial states and the transition relation formula, with the property defined as decision is always made at most on a single value. So the procedure starts with creating a finite instance of the protocol by restricting each protocol sort to a finite set of constants. That is, toy consensus 333 here means we have 3 nodes, 3 quorums, and 3 value constants. The benefit we get is the state space is now finite and quite small, with just 12 Boolean variables. The next step is we perform incremental induction over this finite instance. Let's say during incremental induction we encounter a clause like clause 1 here. This clause has 2 value constants, v1 and v2. Since the domains we are dealing with are symmetric, we can apply all the permutations to this clause and learn all the symmetrically equivalent clauses. That is, we can apply the 6 permutations over the value constants to generate a set of symmetrically equivalent clauses referred as the clause orbit, and therefore learn all of these symmetrically equivalent clauses together instead of learning a single clause, that too without any additional solver reasoning. Next, we encode this clause orbit compactly as a single quantified clause. To do so, we have two requirements: correctness and compactness. Correctness requires that the quantified clause should be logically equivalent to the clause orbit. Compactness requires that the number of quantifiers in the clause should be independent of the finite instance size. Correctness ensures that the finite incremental induction procedure is always guaranteed to be correct, while compactness ensures that whatever learning we are performing is not specific to the current instance size and it generalizes to the unbounded protocol as well. For example, the orbit of clause 1 is compactly encoded with two universally quantified variables like what we have here. Let's try to understand this relation between symmetry and quantification a little bit better. Both symmetry and quantification are equivalent ways of expressing the same thing. If we take this quantified clause and instantiate it for this finite domain, we get 9 clauses as shown here. 3 of them trivially simplify to true, while each of the remaining 6 clauses have a corresponding permutation that makes it symmetrically equivalent to this original clause 1, and together exactly the same as the clause orbit. This ensures correctness and further compactness, since the quantified clause has just 2 quantified variables. Now consider clause 2 as shown here. It has all 3 value constants v1, v2 and v3, and further all of these sort constants appear identically in the literals of the clause. That is, permuting the constants does not give any new logically distinct clause. It simply rearranges the literals, and hence the clause orbit has just a single clause. If we use universal quantification, we would require 3 quantified variables, which violates compactness. That is, the number of universal quantifiers required will increase as we increase the value domain size. Intuitively, this means that if we increase the domain size to say 4 values, the clause orbit will expand horizontally and not vertically, and therefore inferring an existential quantifier is the right way to compactly encode the clause orbit. Similarly, if all except a few sort constants appear identically in the clause, like clause 3 here, where value v1 appears differently while v2 and v3 appear identically, we get an orbit with 3 clauses. And here we perform for all exist inference, where we infer a for all for the differently appearing constant and then exist for the remaining. Our paper has much more details, including the complete algorithmic procedure to perform symmetry-aware clause boosting and to infer the required quantifiers correctly and compactly. Even further, we can extend the quantifier inference beyond these quantified forms by taking the protocol structure into the account. We can use the definitions like did not vote at and chosen at, already present in the protocol description, as auxiliary variables during symmetry-aware incremental induction. This is routinely done in hardware verification, where these are referred as wires in the hardware domain. For example, the decide action can be viewed as a logic circuit, as in hardware. The universals here is an AND gate and the existential is an OR gate. And with these definitions, now suppose we have clause 4 as shown here. It has both state variables as well as auxiliary variables. We can perform symmetry-aware clause learning with any quantification form as per the requirements of the problem by exploiting the already present structural information. For example, once we get the quantified form, we can substitute the definition of chosen at with its definition here to get an overall quantified form as for all exist for all. Overall, for the toy consensus 333 finite instance, we get a quantified inductive invariant with two strengthening assertions A1 and A2 inferred from the clauses small a1 and small a2 as shown below. The next step is to algorithmically check if the finite domain invariant works for the unbounded domain by checking whether the protocol behaviors have converged or not. As noted in several previous works on verification of parameterized systems, protocol behaviors converge once we reach a cutoff size. Beyond this cutoff size, the finite proof also becomes a proof for any size, that is, for the unbounded protocol, since increasing the size beyond the cutoff does not add any new behaviors. But the natural question that arises is, how do we reach this cutoff size? Inspired from mathematical induction over multiple variables, we propose an algorithmic way to reach the cutoff size. Let's say we start with an initial size of 332 for toy consensus, that is 3 nodes, 3 quorums and 2 values. And let Symmetry return an invariant inv332. Of course, by construction, this invariant has to be an inductive proof for this size. We further check, is the invariant still an inductive proof for the next higher sizes? That is, if we add a node, is in332 still an inductive proof? If yes, that's good. And we move on to the next dimension, that is, increase the value domain. If it fails, this means we haven't converged and haven't reached the cutoff yet, and therefore we must repeat Symmetry with now 3 values, because increasing the value domain added more behaviors which we have not considered yet. So now we have 3 values in the value domain, and we repeat the Symmetry procedure. And let's say we get a new inductive invariant inv333. We repeat the convergence check like before. That is, we add a node. Is it still an inductive proof? Yes, it is. Next, increase the value domain. Yes, it is still inductive. Now what this means is that we have converged and reached the cutoff. Adding a node or a value does not add any new behaviors that we haven't seen before, and therefore we have an inductive proof that works for any size. So this is what IC3PO does to verify the unbounded distributed protocol fully automatically. It performs finite model checking along with the concepts of symmetry and quantification, and further checks for convergence. It will auto increase the size if needed, and eventually either produce a counterexample trace that disproves the property or a quantified inductive invariant that proves the unbounded protocol to be safe. Now let's experimentally evaluate IC3PO against other state-of-the-art automatic verifiers for distributed protocols. I4 is a previous work that performs finite domain model checking with the AVR hardware verifier, followed by generalizing the inductive invariant produced by AVR into an unbounded proof. UPDR, also called as PDR for all, performs incremental induction in an unbounded domain. Both I4 and UPDR only support universally quantified invariant generation. FOL IC3 performs enumerative search among different quantification prefixes using a separators-based technique while performing incremental induction in the unbounded domain. Swiss, on the other hand, is a very recent technique that also enumeratively searches for candidate invariants in an optimized and reduced invariant search space. The main difference in IC3PO against these tools is that IC3PO does not search for a particular quantified form or enumeratively searches for different forms. Instead, it uses the protocol structure and the concepts of symmetry to identify the required form by correlating symmetry with quantification. We used all these tools in their default configurations in our experiment and used the same setup for all these tools. 1 hour timeout, 32 GB RAM limit, and included the benchmark suites that are presented in all these different tools. Totally 42 of them. These include two-phase commit, chord ring, reliable broadcast, etc. In terms of number of problems solved, IC3PO outperformed the others significantly and also solved few very challenging problems uniquely, that is, not solved by any other tool. Now let's compare the runtime performance of these different tools. Here we have a cactus plot presenting a runtime comparison. On the x-axis we have the number of problems solved, the more the better, and on the y-axis we have the runtime in seconds, the less the better. Overall, IC3PO solves all 42 protocols in much less time compared to other tools and is much faster. Now, if we compare IC3PO versus i4, we get a clearer picture of the advantages of symmetry-aware learning. Here we compare the total number of SMT queries made by the tools. For the problems that are solved by both the tools, the lower numbers are better. Even though both these tools are using finite model checking, IC3PO makes orders of magnitude of fewer SMT calls, thanks to symmetry boosting. This shows the advantages of symmetry-aware learning, which helps in scalability drastically. Now let's compare the size of the inductive invariants compared to human-written invariants, that is, the number of clauses in the inductive proof between manual proof and auto-generated proof from IC3PO. Again, the low numbers are better. IC3PO finds compact invariants very much comparable to the human-written ones and even smaller in several cases, as shown by the long black lines on the right here. Complete details and evaluation artifact is available in the paper for an independent comparison. Overall, the experiments confirm our main objective. It is possible to fully automatically prove distributed protocols beyond the current state of the art by using symmetry and regularity in these domains. Our current and future work includes dealing with non-symmetric domains like integers. Here as well we can use a different kind of regularity and boost the clause learning. Also, we can use the design structure to derive the inductive proof incrementally through refinement by adding complexity in stages, the same way as experts like Lamport design a complex system in stages. And further in the future, we can extend the approach to other kinds of parameterized systems like cache coherence, neural networks, etc. So if you missed some of the details here, that's fine. Just remember this brief summary. We can verify distributed protocols fully automatically without any undecidability issues with high scalability and derive compact quantified inductive invariants by using finite domain model checking and understanding the relationship between symmetry and quantification, and incrementally increase the size and reach cutoff. We also get provably correct securities and guarantees with independently checkable proof certificates and counterexample traces, with a very general approach that finds applications in a variety of different domains. The tool is open source on GitHub and the extended paper is available on arXiv. Hope you like this talk and also like the tool IC3PO name. This is the end of my presentation and please feel free to ask any questions.